Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, I will explain to you quality of service routing. In the next lecture, we will explain IP switching, MPLS, and GMPLS. In the previous lecture, we have explained different topics related to IPv4 and IPv6. Based on what you have learned previously, try to answer the following questions. First, how many bits IPv4 address consists of? How many bits IPv6 address consists of? IPv4 addresses categories are unicast, multicast, and broadcast. List and explain briefly the categories of IPv6 addresses. What are the techniques available for the transition between IPv4 and IPv6 networks? And the last question, what is the future of IP addressing? In the coming slides, we will give you a background about quality of service attributes, quality of service routing classification, quality of service routing categories, basic framework, and routing protocol used for quality of service routing. On the internet and in other networks, quality of service is the idea that transmission rates, error rates, and other characteristics can be measured, improved, and to some extent guaranteed in advance. Quality of service is an important issue in any communication network. Typically, this can be viewed from the perception of service quality. Eventually, any service perception needs to be mapped to network routing, especially since quality of service guarantee is required for a particular service class. Quality of service refers to traffic control mechanisms that seeks to either differentiate performance based on application or network operator requirements, or provide predictable or guaranteed performance to applications, sessions, or traffic aggregates. To understand quality of service, we will first consider a network link. No routing is considered at this point. We assume that a request arrives at this network for a 1 megabit per second constant data rate. If the network link had bandwidth available that is more than 1 megabit per second, then it can certainly accommodate this request. Thus, the arriving request received the specified quality of service needed. The default service in many packet networks is to give all applications the same service, and not to consider any service requirements to the network. This is what we call it a best effort service. Whereas the basic function of quality of service routing is to find a network path which satisfies the given quality of service constraints and optimize the resource utilization. Who needs quality of service? What kind of application needs the quality of service? Video and audio conferencing require bounded delay and loss rate. Video and audio streaming requires bounded packet loss rates. Time-critical application in which bounded delay is considered to be an important factor. And valuable applications should be provided better services than less valuable applications. Safety critical applications such as remote surgery where the availability issue can be dangerous. In this example, you can see a patient having a surgery performed remotely by a surgeon who is maybe in another city or even in another country. Failure in obtaining the needed quality of service during the surgery may be life-threatening for the patient. The second example is about online games where real-time lag can be a factor. If required quality of service is not achieved, then the player might lose the game, and this is something that the player does not want to happen. An arriving request for resource guarantees might be interested in 1. Bandwidth guarantee, 2. Delay bound, 3. Delay jitter bound, 4. Unacceptable packet loss. Let us explain these parameters that we have mentioned in the previous slide. The first one, bandwidth guarantee. It refers to guaranteeing a certain amount of data can be transferred from one point to another within a network in a specific amount of time. The second parameter, delay bound, which refers to end-to-end delay being bounded. Here we have two types of delays. One-way delay, which describes the time lapse it takes for a packet to arrive at the destination host. The second type, round-trip delay, which measures the time lapse between when the packet gets to the destination host and the receiver to send it back. The third parameter is the jitter. Jitter requires a bit of explanation. It is defined as the variation in delay of received packets. In a packet-based network, packets that are generated at equal spacing from one end may not arrive at the destination with the same spacing. This is because of factors such as delay due to scheduling and packet processing at the intermediate routers, interaction of many flows, and so on. In real-time interactive applications such as a voice or video, the inter-packet arrival times for a call are equally spaced when generated from the sender side, but they may arrive at the destination at uneven time spacing. Thus, the inter-packet delay is known as jitter. The fourth parameter, packet loss, which refers to the probability of a packet being lost along the path from the origin to destination. In the figure, you can see the ping command being used to ping www.google.com. 4 packets were sent and 4 replies were received. One of the values obtained by the ping command is the round-trip delay time. Quality of service-based routing is defined as a routing mechanism under which paths for flows are determined based on some knowledge of resource availability in the network, as well as the quality of service requirement of flows. Or it can be defined as a dynamic routing protocol that has expanded its path selection criteria to include quality of service parameters such as the available bandwidth, link, and end-to-end path utilization, node resource consumption, delay and latency, and induced jitter. So here we have more than one definition for the quality of service routing. The figure shows a simple example of quality of service-based routing. Suppose there is a traffic flow from node A to node C, which requires 4 mega bandwidth. As we can see, although path APC is shorter, it will not be selected because it does not have enough bandwidth. Instead, path ADEC will be selected because it satisfies the required bandwidth, which is 4 mega at least. We have two relevant concepts: policy-based routing and constraint-based routing. The policy-based routing commonly means that the routing decision is not based on the knowledge of the network topology and metrics, but on some administrative policies. For instance, a policy may prohibit a traffic from using a specific link for a security reason, even if the link has enough bandwidth and low delay. Policy-based routing is usually statically configured by the administrator. Constraint-based routing is a new concept, which is derived from the quality of service-based routing, but has broader sense. It means to compute routes that are subject to multiple constraints, including both quality of service constraints and policy constraints. Both quality of service-based routing and policy-based routing can be considered as special cases of constraint-based routing. Now try to answer the following questions based on what you have learned in the previous slides. What is quality of service? What is the best effort service? Where quality of service is needed? What are the quality of service parameters? Give a definition for the quality of service-based routing. It is quite possible that a network might not have the functionality to guarantee that it can meet quality of service for an arriving request, but yet has the resources to meet the request. An IP network without integrated service functionality falls into this category. For example, a voice over IP call can receive quality of service in an IP network without the network explicitly having the ability to provide a guarantee at the time of the request arrival. This can be possible if the network is engineered properly or over-provisioned. Now, in general, over-provisioning is not desirable because the network does cost real money in terms of capacity cost, switching cost, and so on. Similar to the best effort traffic services, the quality of service routing can also have two components, the intra-domain and the inter-domain. These will be discussed later on. Current Internet routing protocols such as OSPF, RIP, BGP are called best effort routing protocols. They use only the shortest path to the destination. In other words, they normally use single objective optimization algorithm that only consider one metric bandwidth, hop count or cost. So all the traffic is routed to the shortest path, even if some alternative paths exist. One drawback of this scheme is that it may lead to the congestion of some links, while other links are not fully utilized. Another thing that the best effort routing will shift the traffic from one path to a better path whenever the better path is found. This happens even if the currently used path meets the service requirements of the traffic. Of course, this will cause routing oscillation when the routing is based on metrics such as available bandwidth, which changes rapidly from time to time. The main objectives of quality of service-based routing are: the first one, is to meet the quality of service requirements of end users. Quality of service-based routing is supposed to find a path from source to destination which can satisfy users' requirements on bandwidth, end-to-end delay, and so on. This should be done dynamically. Now, in case there are several visible paths available, the path selection can be based on some policy constraints. The second objective of quality of service-based routing is to optimize the network resource usage. This is usually an objective from the service provider point of view. Every service provider wants to maximize the utilization of their current network facilities, and thus to maximize its revenue. The quality of service-based routing is expected to direct network traffic in an efficient way that can maximize the total network throughput. One common scheme is to always choose the shortest path among the visible candidates, because the longer path means using more network resources. The third objective of quality of service-based routing is to gracefully degrade network performance when things like congestion happen. When network is in heavy load, quality of service-based routing is expected to give better performance than best effort routing. Quality of service-based routing is much more difficult to design and implement than best effort routing. Many trade-offs have to be made. The goal here is not to find the best solution, but rather to find a viable solution with acceptable cost. Following are the issues of quality of service-based routing. First, metric and path computation. Two basic issues of quality-based routing are, first, how to measure and collect network state information. Second, how to compute routes based on the information collected. Metric selection is very important in the sense that the metrics must represent the basic network properties of interest. Thus, metrics like available bandwidth, delay, jitter are commonly used. The second issue, knowledge propagation and maintenance. One important issue is how often the routing information is exchanged between the routers. Quality of service-based routing needs to exchange more information compared to best effort routing. First, beside the routing information needed by best effort routing, quality of service information such as available bandwidth needs to be exchanged too. Second, the metric used by the quality of service-based routing could be changing very quickly. The third issue, scaling by hierarchical aggregation. This issue is related to path computation and information propagation maintenance issue mentioned above. Considering the size of the internet, quality of service-based routing is expected to be scalable. With the number of nodes and links in the network increasing, the complexity of path computation and the amount of information needed to be exchanged and maintained won't be out of control. The fourth issue, imprecise state information model. A trend in quality of service-based routing algorithm design is that more and more people realize the imprecise nature of quality of service routing. Imprecision means that the routing state information based on which the routing decision is made is not accurate or precise. The fifth issue is the administrative control. There are some control issues regarding the quality of service. The first one, flow priorities and preemption. Different flows in the network have different quality of service requirements. Thus, they should have different priorities. Critical flows can be assigned higher priorities than the other flows. When the resources are not enough, such flows can preempt the resources from flows with lower priority. For instance, a voice or video flow can be assigned higher priority and is allowed to preempt bandwidth or buffers from FTP flows. The second thing is the resource control. In the network framework, which has multiple service classes of traffic differentiate service, for instance, the resources should be allocated fairly among all the classes. Thus, starvation of lower priority classes can be avoided. This allocation can be done in a dynamic fashion. The last issue is to integrate quality of service-based routing and best effort routing. For compatibility, quality of service-based routing must be able to support best effort routing too. This means these two routing schemes must be able to coexist. One question here is how to allocate network resources between them. We should have overall control so that the quality of service-based routing does not use too much of the resources. Otherwise, best effort traffic would have virtually no resources to use. Many different quality of service-based routing have been proposed in recent years for both unicast and multicast routing, with most of them concentrating on one particular problem. These algorithms have different assumptions of the network condition and thus cannot work together. Then it is realized that a common framework is needed, which can accommodate different kinds of algorithms. The RFC 2386 provides such a framework, which has two levels: the intra-domain quality of service-based routing and the inter-domain quality of service-based routing. This hierarchical model is compatible with the routing hierarchy of today's Internet. The figure here shows such a two-level routing structure. The routing between the nodes A, B, and C belongs to the intra-domain routing, while that between node B and E or B and F, it belongs to the inter-domain level. For intra-domain quality of service-based routing, it is intended to accommodate many different algorithm schemes in one domain. The network manager should have the freedom to use whatever quality of service-based routing inside the domain, which is independent of the quality of service-based routing used in other domains. Here, diversity is encouraged at this level. Quality of service-based routing service can range from dynamic path computation based on the current state information to statically provisioned paths supporting a few service classes. Some common features are required for intra-domain quality of service-based routing. They are listed as follows. 1. The routing scheme should find path which can meet the quality of service requirements of the flow if such a path exists. Otherwise, it should indicate that the flow cannot be admitted. 2. To optimize resource usage, the routing scheme must indicate path disruption whenever the path is affected by topological changes of the network. 3. The routing scheme should support best effort flows, which doesn't have any resource reservation requirements. In other words, current best effort application and protocols need not to be changed in quality of service-based routing domain. 4. The routing scheme is expected to support multicast quality of service-based routing with receiver heterogeneity and shared reservation styles. 5. The routing scheme should have higher level admission control to limit the overall resource utilization by individual flows. In contrast, inter-domain routing is expected to be as simple as possible. Stability and scalability are the most important issues at this level. The routing cannot be based on highly dynamic network state information, but instead, the quality of service information exchange between different routing domains should be relatively static. The inter-domain routing scheme must have the following basic functions. 1. Determination of whether a destination is reachable. 2. Avoid routing loop. 3. Support address aggregation. 4. Determination of whether the quality of service requirements can be supported on the path to a destination. 5. Determination of multiple paths to a given destination based on service classes. And 6. Mapping routing policies to flow metrics. So these are the basic functions of the inter-domain routing scheme. Most of the quality-based routing algorithm proposed belong to the intra-domain level, not to the inter-domain level. It belongs to the intra-domain level. Based on what you have learned earlier, try to answer the following questions. What are the objectives of quality of service-based routing? What are the issues of quality of service-based routing? Can you explain them? What are the features of intra-domain quality of service-based routing? What are the features of inter-domain quality of service-based routing? Most of the quality of service-based routing algorithms proposed belong to the inter-domain level. Is this statement true or false? The characteristics of an ad hoc network pose several challenges in the provision of quality of service. Some of these challenges are as follows. 1. Dynamically varying network topology. Since the nodes in an ad hoc wireless network do not have any restrictions on mobility, the network topology changes dynamically. The admitted quality of service sessions may suffer due to the frequent path breaks, thereby requiring such sessions to be re-established over new paths. The delay incurred in re-establishing a quality of service session may cause some of the packets belonging to that session to miss their delay target or deadline. 2. Imprecise state information. In most cases, the nodes in an ad hoc wireless network maintain both the link-specific state information and flow-specific state information. The link-specific state information includes bandwidth, delay jitter, loss rate, error rate, stability, cost, and distance values for each link. Whereas the flow-specific information includes session ID, source address, destination address, and quality of service requirements of the flow, such as maximum bandwidth requirement, minimum bandwidth requirement, maximum delay, and maximum delay jitter. The state information is inherently imprecise due to dynamic changes in network topology and channel characteristics. Routing decisions may not be accurate, and this will result in some of the real-time packets missing their deadlines. 3. Lack of central coordination. Mobile ad hoc networks, MANETs, they do not have central controllers to coordinate the activity of nodes. This further complicates the quality of service provisioning in MANETs. 4. Hidden terminal problem. The hidden terminal problem is inherent in MANETs. This necessitates retransmission of packets. 5. Limited resource availability. MANETs have limited resources such as bandwidth, battery life, storage, and processing capability. They have to be utilized in a very efficient way. Efficient resource management mechanisms are required for optimal utilization of these resources. 6. Insecure medium. Security in a wireless channel is less. Due to the broadcast nature of the wireless medium, security is an important issue in MANETs, especially for military and tactical applications. MANETs are susceptible to attacks such as spoofing, denial of service, and message distortion, and so on. Without sophisticated security mechanisms, it is very difficult to provide secure communication guarantees. Below are some basic requirements for quality of service-based routing algorithms. 1. Efficient and scalable to large network. 2. Complexity not far greater than the current used routing algorithm. 3. Suitable to current internet architecture. Note that some of them are conflicting with each other, so that compromise has to be made. On one hand, we need efficient algorithms, and the algorithms should be scalable enough that they can be used in the internet. On the other hand, these algorithms should not be too complicated. We have to make some trade-offs between efficiency and complexity. Quality of service-based routing algorithms are expected to be employed in the current internet. They must be easy to implement. They must be compatible with the current best effort routing. In other words, they do not require the modification of current internet applications and routing protocols. Here, we will give two examples of quality of service-based routing protocols. The first one is the QoSPF, is an extension to OSPF into which quality of service functions are added. OSPF is also based on linked state algorithm and is hierarchical protocol. The design goal of the QoSPF is to define an approach which, while achieving the target of improving performance for quality of service flows, it does it with the least possible impact on the existing OSPF protocol. It is supposed to be working in an environment in which both quality of service based routing and best effort routing are needed. The second one, the ATM private network-to-network interface, is a hierarchical dynamic routing protocol for ATM network, which supports the quality of service naturally. This protocol is based on linked state algorithm. Topology information, including information about the nodes, links, and addresses, is flooded through the network. Network resources are defined by metrics and attributes such as delay, available bandwidth, jitter, etc., which are grouped by the supported traffic class. Since this routing protocol is hierarchical, it has the concept of levels and logical nodes. It also supports aggregation and summarization of topology and reachability information. The ATM private network-to-network interface has other features such as auto-configuration of the routing hierarchy, connection admission control. This is part of the path calculation. To summarize what you have learned, quality of service routing was defined and why we need it. What are the classifications of quality of service routing? What are the concepts related to quality of service categories? The objectives of quality of service routing? The issues related to quality of service routing? The intra and inter-domain quality of service based routing and their features. The challenges in quality of service routing in mobile ad hoc network. And finally, we gave two examples of quality of service based routing protocols. We come to the end of this lecture. If you have any question or inquiry, then please send an email to your lecturer. Stay safe and God bless you all. Assalamu alaikum wa rahmatullahi wa barakatuh.